Okay, so today we're starting Chapter 3, and Chapter 3 starts off with complex numbers. The majority of Chapter 3 is actually going to be spent doing quadratic functions and polynomial functions and all that kind of stuff. But before we can really talk about all that, we have to have at least a little bit of a grasp on complex numbers. Now, hopefully you guys have seen complex numbers at some point, but in case you haven't, or in case it's been a minute, let me refresh you about some of the different types of numbers. First off, you have your counting numbers. These are the numbers 1, 2, 3, 4, when you start counting your fingers, those are your counting numbers. Those are also known as your natural numbers. Outside of those, we have what are known as whole numbers. Those include your counting numbers, but also the number 0. Those are considered whole numbers. Then you have your integers, and those include the counting numbers and the whole numbers, but then also include the negative, quote-unquote, whole numbers. So -1, -2, -3, and so on and so forth. After that, we have rational numbers. Rational numbers can be any number that can be written as a fraction. So 1/2, 0.66666 repeating. Repeating decimals, terminating decimals, fractions, those are all included in your rational numbers, and so are counting whole integers, because you can write an integer as a whole or as a fraction. Over to the side of rationals is something called your irrationals. Those are very special numbers. Those are like the square root of 2, pi. These are non-terminating, that means they don't end, non-repeating decimals. So notice that you're not a rational and an irrational at the same time. Those circles do not overlap at all. You're one or the other. Outside of those, including both rational and irrational numbers, are your real numbers. If you took Math 20, that's where we stopped. We stopped with real numbers, and we only talked about real numbers. But really what happens is there's kind of like this big box that goes all the way around real numbers that includes this little subsection over here that are imaginary. And the box that includes our imaginary and our reals are known as our complex. So every number you've ever dealt with is a complex number. That's just like the biggest group that we could think of it in. All real numbers are complex. They just don't have an imaginary portion. You can have imaginary numbers and complex numbers which have imaginary parts. So this is kind of like the whole layout of all the different types of numbers that you've ever really encountered. Most math that you've dealt with deals here with the reals. Today we are branching out and including these imaginary numbers over here and thus talking about them in terms of complex numbers. You don't have to memorize all this. I just wanted you to see kind of how numbers are grouped together in math so that you understand where these imaginary numbers kind of fit in and where these complex numbers fit in. So, if we're talking about imaginary numbers, we need to mention the imaginary unit. I is the imaginary unit. It's short for imaginary. I is equivalent to the square root of -1. For years and years, you've had math classes where you can't take the square root of a negative number. And that's true. The reason why you can't take the square root of a negative number is because you don't get a real answer. And when you're only dealing with real numbers, then we have no way to talk about this. But now we're going to introduce the imaginary unit so that we have a way to discuss what happens when we take the square root of negative numbers. And thus we get complex answers. So if I equals the square root of -1, then if you square both sides of that little equation, you can see that I squared is equal to -1. Those two things are very important to memorize. I equaling the square root of -1 and I squared equaling -1 are very important as we move forward. I didn't realize there was an example on here, but there is. There's a simplify example. Let me zoom in a little bit further. Some of your problems will ask you to simplify these radicals where you have a negative underneath. If you aren't super competent in radicals. They were covered in Math 30. And there's tons of resources online for that if you need to go refresh on how radicals work. The Khan Academy, KAHN, is a great online resource that's totally free. It's usually geared towards middle school and under, but you can look it up by topic, and so you could go look up radicals, and it'll give you a quick overview of it, and it's a really good resource. But if we are simplifying the square root of negative 25, then what's really going on is we can break this up into the square root of negative 1 times the square root of 25. Well, we just said the square root of negative 1 is I. The square root of 25 is 5. So this breaks down into 5i. When you write a number or a term that has an imaginary part to it, like 5i, we do usually put the real part first and the imaginary part second. That's also true when we talk about expressions that have complex numbers, like this. The complex numbers is a set of all numbers in the form of a plus bi, where a and b are real numbers and I is that imaginary unit. So there's 3 general examples of complex numbers. Negative 4 plus 6i, that's a complex number. 2i is a complex number. The real part is just 0, and that's okay. The same thing is true for the number 3. 3 is a complex number, it just doesn't have an imaginary part, or 0 is the coefficient of that imaginary part. That's why I showed you that picture of how all the numbers are laid out, because that complex box goes around all the real numbers, like 3, and all the imaginary numbers, like 2i. And it includes all of them. Oops, sorry. That moved a little bit.
I have a question.
Yes.
Is the 2i underneath the negative 4 plus 6i, is that the result?
No.
Okay.
No. These are 3 totally separate examples of...
Okay.
Yeah. I scooted it over because I wanted all the imaginary parts to line up, and I wanted the real parts to line up, so it would make it more noticeable that there was 0 in place of the real for that one. Okay. No, thank you for asking that question, though. That's good clarification. No. The way imaginary numbers, or the way complex numbers work, is you think about them like combining like terms. So we can't combine the negative 4 with the 6i, because the negative 4 is real and the 6i is imaginary. So... that's actually what happens when we are doing adding and subtracting of complex numbers. The little star note over here on the side says you're combining like terms. If I'm adding a plus bi and c plus di, then what I'm really doing is I'm adding the real parts, which are the a and the c, and then I'm adding the imaginary parts, which is the b and the d. Same thing is true with the subtraction aspect of that. So just like with real numbers, we can add, subtract, multiply, and divide complex numbers, and that's what we're going to focus on today, is how do we do all these algebraic operations with complex numbers? Because we can't just add them like we do regular numbers, because they have 2 different parts to them. Up, maybe. Okay. We're going to do one example of adding complex numbers and one example of subtracting complex numbers. The nice thing about adding complex numbers is, like the little star note says, you're just combining the like terms. And I don't have another. So by like terms, I mean we're going to add the real parts So 5 plus 7 will give me 12. And then we're going to add the imaginary parts. We have negative 11 plus 4i will give me a negative 7i. That's all you can do. You can't combine that any further. We're not solving. I is not a variable that we are trying to discover what it equals. I actually stands for a number. It's kind of like pi. You know, if you ever see the number pi, that symbol represents a number, 3.14, blah, 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 blah. I also represents a number. It represents that square root of negative 1. So this is as far as you can take it. Don't try and overcomplicate it. Okay, so when we subtract, it's really the same thing. But you have to be careful about that minus sign. That minus sign in between, we're going to have to distribute it before we can actually combine our like terms. Because we're going to have negative 5 plus I, and then we have a minus minus, which makes it a plus 11. And a minus minus, making it a plus 6i. If you do not resolve that negative situation, if it does appear that way, you will get your answer wrong every single time when it comes to doing subtraction with these problems. Now what we have is we have negative 5 plus 11, which gives you a positive 6. And you have an I plus 6i, giving you 7i. Are there any questions on how we add or subtract complex numbers? I have no idea. Somebody who probably went crazy. That just seems to be a common theme for mathematicians.
Do you think they just gave up on it and then just said that in place of giving up?
No, but I'll research it because I've never had a student ask me where it comes from.
They just solved that fever.
Huh?
They solved that fever. Well, they woke up late one night. Just rushed to the board. They always have a board.
Okay, multiplying complex numbers is next. There are two different ways to multiply complex numbers because it depends on what kind of complex numbers we're talking about. The first way is either to distribute or to FOIL. Or if we're dealing with complex numbers that are in radical form, we also can do just radical multiplication, which again, maybe you haven't experienced or seen for a while, so this is kind of a nice little refresher. So we're going to do these three examples to show you all the different ways you can multiply these. So multiplying complex numbers, distribute or FOIL. Now, some of you may be tempted, especially on this first problem, to just type that bad boy into your calculator. Don't do that. Remember, your calculator is not as smart as you are. And especially when we're talking about imaginary units, what we want to do is we want to pull the imaginary unit out before we do the multiplying. Okay?
4i times 5i.
Yes, that is what we're going to get to. So in this case, if I'm looking at the square root of negative 16, that's the same thing as I square roots of 16. Are we okay with that? Because square root of 16 is the square root of negative 1, times the square root of 16. Well, the square root of negative 1 is I. So that's all I did to get over here. Do we see that? And then I do the same thing for the square root of negative 25. That would be I square roots of 25. Square root of 16 is 4, so that means this is 4i. Square root of 25 is 5, so that means this is 5i. 4 times 5 is 20. I times I is I squared. But what does I squared equal? So this is 20 times negative 1, which is negative 20. If you type the square root of negative 16 times the square root of negative 25, if your calculator is even smart enough to do any of that, what they're going to tell you is you're going to have the square root of, 4,000, I think, which is just 20. Your sign will always be wrong because your calculator is not trying to do it with the imaginary unit. This is why you want to do this on paper, because negative 20 is correct. And here's a word of caution. If you ever get an answer that has an I squared in it, you're not done. I squared can always be simplified because I squared is negative 1. So don't stop if you have an I squared. Keep going with it. The next example is where we're going to use our distribution property that we learned. We have a 4i outside of a 3 minus 5i. Notice inside the parentheses you have a real and an imaginary part of this complex number, so they can't be combined any further. So all we can do is distribute. So we're going to distribute that negative, or that 4i inside. 4 times 3 is 12, giving me 12i. Distribute again, I get a negative 20i squared. But that I squared is negative 1. So I have 12i plus 20. I can't combine those any further, but a rule of thumb is whenever you are writing your complex numbers, you want your real part first, then your imaginary part. So I am going to reorder this so that it says 20 plus 12i. Real part first, then your imaginary part. Are there any questions so far? Okay. This last example down here, we have to do FOIL. FOIL is first, outer, inner, last. It's how we multiply binomial by binomial. So first, I would take 7 times negative 2. That's negative 14. Outer, 7 times negative 5i, negative 35i. Inner, negative 3i times negative 2, positive 6i. And the last will be negative 3i times a negative 5i, giving me a positive 15i squared. Negative 14 minus 29i. Here in the middle, I combine those like terms. And then I squared is negative, so I'm going to have a minus 15. So then I still have like terms of negative 14, negative 15. So this becomes negative 29 minus 29i. Kind of a fun one because it gets pretty much the same thing for both our real and our imaginary parts. I would say almost always, definitely always, if you're taking a complex number times a complex number where you have to FOIL like this, you're always going to have an I squared situation pop up. So just make sure that you are cautious about that. Are there any questions on how we multiplied any of these problems? Okay. Division is where it gets a little bit more complicated. Not hard, just a tad bit more complicated. Because we have to deal with something called conjugates. The complex conjugate is used to get real numbers and to divide by complex numbers. When we think about dividing by a complex number, what really happens is we end up with a fraction, where we have a complex number in the denominator, and we don't like that. There's certain things that we just don't like in the denominators of our fractions. We don't like radicals in the denominators of our fractions, and we don't like complex numbers in the denominator of our fraction. So in order to rationalize our denominator, to get rid of that that complex number in the denominator, we have to multiply it by its conjugate. And that sounds super complicated because you're like, I got to find the complex conjugate. All you have to do is change the sign. If you are given a plus bi as your complex number, the conjugate of that is a minus bi. If you're given a minus bi, the complex conjugate of that is a plus bi. Because what happens then is when you multiply by the conjugate, the I term goes away. Goes away entirely. If you don't believe me, I can show you on this first one, where we have a plus bi times a minus bi. That's a complex number, and we're multiplying it by its conjugate. And if we FOIL, what happens is we take first, so we get a squared, outer, minus abi, inner, plus abi, last, minus b squared I squared. Notice the middle two terms that have the I are going to go away. They're going to cancel. This I squared changes this to a positive, so we have a squared plus b squared. Both of those are real numbers. So we get rid of our imaginary part entirely by multiplying by the conjugate. Sorry, that went off the screen a little bit for you guys. You don't have to prove it. You're going to end up proving it as you rationalize your complex denominators throughout this assignment. So you don't ever want to leave a complex number in the denominator. You don't ever want to leave a radical in the denominator. Those are two good rules of thumb.
So what happens to the negative one? Because it's I squared, it would be negative 1. So where's that going?
Well, this was a negative right here until I made it positive.
Okay.
Yeah, because it was negative b squared, and so with that negative, then it becomes a positive.
Okay.
So let's conjugate a denominator. We have 3i over 4 plus I. We don't want to leave it like this. We got a complex number in the denominator. So what we're going to do is we have to find the conjugate and multiply the top and the bottom by that conjugate, because that will get the bottom to be only a real number and get rid of that imaginary part. So if you like steps, 1, find conjugate. 2, multiply top and bottom by conjugate. That's what we're going to do. So what is the conjugate of 4 plus I? 4 minus I. Yay. So I'm going to take 3i over 4 plus I, and I'm going to multiply the top and the bottom by 4 minus I. So you're going to get really good at multiplying these complex numbers, because on top, we're going to have to distribute, and on bottom, we got to do our FOIL. So we get 12i minus 3i squared all over 16, and it would be a minus I squared, which will be a plus 1. Did I lose anybody on how I got my denominator? The way it works is you're going to have this number squared minus this one squared, but I squared is a negative 1, thus making it a positive 1. You do not have to skip steps. You can write it all out, do it the long form, however it works for you. So we have 12i, this I squared goes to negative 1, changing the sign here, all over 17. So we get 3 plus 12i all over 17. And I am totally okay with that as an answer. I'm not 1,000% sure that that's a totally acceptable answer for your book. In general, when we write complex numbers need to be written as a plus bi, where our real is completely separated from our imaginary, not combined up in a fraction form. That means that a lot of times you'll see it written as 3 over 17 plus 12 over 17i, where they split the fraction up and they really separate the real part from the imaginary part. On a test, I am totally fine with this. I haven't played around in my math lab yet to figure out if they will, which way they prefer it. They will tell you very specifically, because my math lab's really good about that, and I can include it in an announcement later on this afternoon after I've put the assignment up for you.
Is the I outside of the fraction, or is it under with the 17?
It's outside.
It's outside.
Because it resides on top, so I just pulled it down to the side. Questions? I've got another one. Got another division one. Divide 7 plus 4i by 2 minus 5i. Step 1, we got to figure out what the conjugate is. What is the conjugate? 2 plus 5i. So I'm going to multiply the top and bottom by 2 plus 5i. And that means on top I'm going to have to FOIL because I have a binomial times a binomial. The bottom is going to end up being 2 squared plus 5 squared. Top will have 14 plus 35i plus 8i plus 20i squared. I'm going to combine those middle two terms for 43i. I squared is negative 1, so I'm going to have minus 20 all over 4 plus 25. Negative 6 plus 43i all over 29. And if we split that into real and imaginary parts, you'll get, sorry, I didn't realize it was so crooked.